Hello everyone. Today we're going to be learning about functions. So functions are simply an expression that relates inputs to outputs. So as you see here, we have our input that's getting passed into our function here. And our function simply spits out a respective output for that input. So in other words, for each input, typically denoted as x, our function has a single output denoted y. Now, functions are typically given in forms of y equals x to the fourth plus so on and so forth. I'm sure you've seen this before. And they're also given in the form y equals f of x equals x to the fourth again, yada, yada, yada. Either one of these is interchangeable. As you can see here, our input's x. So we input x and we get a respective y for each input. Now, we need to talk about why exactly do we care? Because this is a calculus lesson. Why do we care about functions? Well, calculus is essentially just the study of functions. So if we don't have a good understanding of functions and what they are, once we introduce calculus, we're going to be completely lost here. So this is great foundational content to be learning. So let's look at a stock price, for example. This is a great example of a function. So our input in this case is going to be time, which is on the x-axis, and our output is going to be the specific stock price at that time. And our function you can think of as the stock market as a whole, the amount of buyers or sellers that are driving the price, right? So on the left-hand side, let's say we have T0, T1, and T2. At input T0, our price is going to be roughly here, and let's say that's 100. So at T0, and we'll label it as F of T0, is roughly 100. F of T1, so at time 1, our price is up here, let's say 150. So again, input T0, T1, output 100, 150. And lastly, F of T2, outputs, let's say 175. Okay? Now another example here, same thing, stock market price, just on a downturn. So we got T0, T1, T2. Hopefully you've never seen this before, right? So if we've got F of T0, which is right here, we're getting, let's say, 190. F of T0 is 190. F of T1 is 180, let's say. And T2, let's say this is 100, so F of T2 is 100. All right? So here's some actual examples in regards to y equals. So what we can do for each of these, I'm going to plug in x equals 0, 1, and 2, and we'll see how we get our output. So let's start with the left-hand side here. If we plug in 0, we get 0 to the third, which is 0, plus 2 times 0 is 0, plus 5. So I'm going to write f of x, which is f of 0 in this case, equals 5. F of 1, we plug in 1. 1 cubed plus 2 times 1 plus 5 gives us 1 plus 2 plus 5 gives us 8. And f of 2, lastly, gives us 2 cubed plus 2 times 2 plus 5. So this is 8, this is 4, and this is 5. So that gives us 17. All right. So hopefully you can see, very similar to the stock market price, we take our input x and get our respective output y, or f of x. Okay? You can also write these as coordinate points. So for example, we've got x comma y. So you could do 0 comma 5 for this function again. 1 comma 8 and 2 comma 17. Okay? Let's look at this function on the right. Again, same inputs. So f of 0 equals 0 squared plus 4 gives us 4. F of 1, plug 1 in for x, 1 squared plus 4 gives us 5. F of 2 gives us 2 squared plus 4, which is 8. Okay, again, simply just mapping our inputs to outputs. And in coordinate form, it would look something like this: 0, 4, 1, 5, 2, 8. All right. Now, there's a way to determine whether or not a function is a function or not based on looking at the graph. This is called the vertical line test, which states that if you draw any vertical line at any point, that vertical line can only intersect the function at most one time. So it doesn't have to intersect, but if it intersects it 2, 3, 4 or more times, it is not a function. So if we draw a vertical line through this function, f of x equals x squared, regardless of where you draw that vertical line, you will see that we only intersect the function once, meaning that this indeed is a function. Let's look at this example. F of x equals x cubed. Again, vertical line here, intersect it once. Here, intersect it once. So this indeed is a function. Now, another example, f of x equals absolute value of x. Regardless of where you draw this vertical line, you're only going to intersect the function once. So again, that's functions. So these first three are in fact functions. Now lastly, we've got a circle here. X squared plus y squared equals 16. If we draw a vertical line here, we intersect here. Keep going. We intersect there again. You'll see anywhere that we draw a line, we're going to intersect it twice. Or you could draw it outside, but again, if at any point you intersect it more than once, it's not a function. This one is not a function. All right, so even functions are simply functions with the property f of x equals f of minus x. What does this mean? Well, it simply means that they're symmetrical across the y-axis. So I've gone ahead and drawn three examples here. As you can see on the left-hand side of the y-axis, I'll label the y-axis as so, x and y. So the way I like to think of it is if you folded this half of the plot over, it would completely overlay this half, which is another way of just visualizing that symmetrical property that these functions have. Again, you take this right-hand side of the graph, flip it over, you'll see it overlays perfectly. So these first two are even functions. And lastly, f of x equals 5, just a straight line. If we take this half of the plot, flip it over, you'll see that it perfectly overlays, meaning that this is an even function. Okay, now we're going to look at odd functions. So odd functions are just functions that have this property here, negative f of x equals f of minus x, which this just means that these functions are symmetric about the origin. Now, the way I like to visualize this is if you rotate the graph 180 degrees, it will look the exact same. If that's the case, they are odd. Okay? So if you it's kind of hard for me to draw, but let's look at f of x equals x cubed first. So we've got something like this, right? Now, if we rotate it 90 degrees, we'll have something like that. And if we rotate that another 90 degrees, we'll have something that looks like that, which, hey, you'll notice that looks exactly like this function right here, right? So this is an odd function, which also can apply to f of x equals x to the fifth. Exact same shape, rotated 180 degrees. You'll see it looks the exact same. And f of x equals x, again, same principle. That intersects the origin there. Rotate it 180 degrees. You'll see that it looks something like that. Okay? Now, one last thing we need to touch on is the fact that some functions are neither even or odd. They don't have to fall into one of those categories, which a lot of people get mixed up. Let's say we look at the function f of x equals x cubed minus 1. Very similar to the one we just looked at, except it's dropped down by 1. So if we rotate this 180 degrees, it's going to look something like that, right? So it's above the origin, whereas this one's below the origin. Okay? And a very similar example here, we've got X shifted up 4. So if we rotate that 180 degrees, it'll look something like that. Okay, so these have no symmetrical properties. They're not symmetrical. You know, if you tried folding this over, you'd see, hey, that doesn't overlay this. So not even. Again, same thing here. Overlay that. That's not even close to overlaying this. And if you rotate them 180 degrees, you'll see they're different. So not every function has to be even or odd.